Okay, so Wednesday, that was our last class. Wednesday, we did 7.1, which was on oblique triangles and the law of sines. And basically, we learned how to solve triangles that aren't right triangles. That's what we did. And we used the fact that our interior angles add up to 190 degrees. And then we used our newly learned law of sines, where the side over the corresponding sine angle were all equivalent. And we did a problem or two dealing with the area of a triangle as well, again using our law of sines to come up with anything that was missing there. And that's what we did in 7.1. And we had these different congruency axioms that you probably saw way back in geometry, back in high school, where these were ways that we could say two triangles were congruent, as if we knew, the angle side angle, or side angle side, or side side side, or side angle angle. If we knew that information, we could determine that two triangles were congruent. Notice that we couldn't do angle, 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 because that just told us that triangles were similar. And also, maybe you remember, because it was always the most widely discussed and desired axiom, would be angle side side, because then you have your ass angle, and that one never came up. That's not here. You didn't have it in high school either, and that was one of the ways you knew that one wasn't a congruency. And the reason why is because it actually doesn't show us that something is congruent. And this table on the handout shows you why. Because if you know side angle, or side angle, or the other way of angle side side, you actually don't have enough information to make a full triangle. You just don't have enough. And so we can't do law of sines, we can't do congruency or anything with it because we don't have enough information. Because all of these triangles right here have side angle, all of them. And they all look completely different. And so we are going to learn today in 7.2, it's called the ambiguous case of the law of sines. And that's where we deal only with side angle triangles, or ass triangles, if you want to read them the other way. So there is lots of different things that can happen depending on the measures that we do know. So we can have acute triangles, which is what you're going to see more times than not. And then there's a couple cases where they are obtuse. And when we are dealing with these, because there's so many different possibilities, sometimes we can get no triangles out of it because it just doesn't work. It's never going to connect. Those side links are not going to connect up to make a triangle. That happens here when we have an acute. It can also happen when we have an obtuse. Notice that the side A is incredibly short and is never, ever going to touch down on either side of these triangles. And so there's a chance that we're not going to get a triangle that works at all. There's the chance that you're going to see more times than not, which is where one triangle will work and we're able to deal with it just like normal. And then there is one rare case where there's actually two triangles that work. And we're going to do an example of that. So those are kind of all the different cases and scenarios. You don't have to memorize these. You don't have to memorize, what happens on the right-hand side or anything like that. It's just good to know that as we are approaching these ass triangles, that there's a lot of different ways that these can show up. Okay? They don't play nice. They're ambiguous. They're oblique. So these are kind of really weird triangles. But we can still solve them for the most part. So how do we do that? Well, that's what the bottom little section is. And yours are not green. Yours are all printed out in black and white. When we apply the law of sines for any angle theta of a triangle, if the sine of that theta lies between 0 and 1, that's when we can do it. Because remember, sine is limited to 0 to 1. Think of your unit circle. If sine theta equals 1, then theta has to be 90 degrees, which means we have a right triangle, and that's what we've dealt with almost the entire semester. Otherwise, we're going to have to come up with the supplementary angles. The smallest angle is opposite of the shortest side. The largest angle is opposite of the longest side, and the middle angle is opposite of the intermediate side. That's what it's going to come into. Now, it gives you all of that information. I don't think it's super helpful. I think just working through some of the problems and seeing how these play out is what's really helpful. That's why I made a handout with all of this information, which is great reference, not totally applicable all the time. Okay, so let's look at what's going to happen. Because that's a different page. On Wednesday, we learned that if we want to solve a triangle, we have to find all of the missing parts. So if we are given certain information, like we know side B, we know side A, and we know angle B for this problem, that means we're going to need to come up with angle A, angle C, and side C. Those are the three missing parts that we have to come up with because it says solve the triangle. And so we're going to use any and all information that we have to try and solve this triangle. We're not even going to draw the triangle. I did draw a triangle at the very end to kind of show you what happens, but that's about it. We're going to approach this just like we did from the 7.1 material. So we're going to try and find all of the information that we can, and then we're going to see if that happens to lead us to an actual solution where we solve it just like we did on Wednesday, or if it leads us to where we actually could have two different solutions. That's one of those options. Or there was the option that a triangle really can't be made because our side lengths are never going to connect up. And looking at it from the beginning, you're not going to know that. We have to work through it. So if we know side B and angle B and side A, what is the first thing that you think we can find next? Yeah, we can find angle A, because remember from our law of sines, we know that A over sine A equals B over sine B. And out of this proportion, we know 3 out of the 4 values. So yes, we can find angle A. So A is 25.1. We don't know what angle A is. That's what we're going to find. B is 8.94, and angle B is 55 degrees 40 minutes. Now obviously we're going to have to convert the minutes, but we can wait to do that for a little bit. So let's get sine A all by itself. We do that, we can do cross multiplication. 8.94 sine A. Remember, you always want to wait until the very last step, if possible, before you do any type of rounding. $25.1. All over the 8.94. So remember, if we need to convert from minutes to degrees, there's 60 minutes in a degree, so you'd have the 55 plus 40 over 60, which is going to give you the 5.666, however many times you want to write 6, because it goes on for forever. But that's what you're going to want to type in. So we find that sine of A is approximately 2.31844. But what do we know about sine? If you don't know anything about sine, try doing sine inverse of what you just got and see what your calculator tells you. What do you get? Huh? An error. You get an error. Sine has to live between 0 and 1. We just got sine is 2.31 blah, blah, blah. That's too big. So what this tells us is that there is no triangle for this. We have one of those cases where our sine is greater than 1. And if our sine is greater than 1, regardless if we have an acute triangle or we have an obtuse triangle, that's the two situations where we are not going to get a triangle that makes it all. Because when we go to try and draw this, which my drawing's not super great, but if we try to draw this in at all with our degrees of 55, we have this is 25, this is 8. Like, this is so scrawny, it's never going to connect up because of the angle that we have. And so we have a triangle that can't exist based on the limitations that they gave us. And we discover that pretty quickly because we get a sign that is too small or too big to actually be a sign that we have. So if you get sine of your angle is greater than 1, you're done. It doesn't work. There's no triangle that works for this. And that's one of those cases. This one's an acute version, and we know it's an acute version because it told us that B is 55 degrees. You could get the exact same process if they had told you that B is 155 degrees. I'm not saying that necessarily works in this case. I'm just saying that's what the obtuse one would look like. It's just a fatter version of the triangle. So no triangle exists. Questions? When we get one triangle that works, it really works just like it did on Wednesday. And we're going to get one that works in just a little bit where it's just one triangle. But I started off with one that doesn't exist, and then I'm going to show you one where we're going to get two different triangles because these are completely different than the things that we've already encountered in Chapter 7. So, let's solve another triangle. This one we're not going to have to do any type of converting in terms of our minutes because I didn't think that that was necessary. We're going to solve triangle ABC, knowing that angle A is 55.3 degrees, side A is 22.8 feet, and side B is 24.9 feet. So this one's actually pretty close to the problem we just did. If you're looking at like the amounts and things, our angles are almost the same. One of our sides is almost the same, but it's the other side that is substantially bigger in this new triangle. Side A is 22 feet instead of almost 9 feet. And that's going to make a big difference in how this triangle plays out. So we're going to do the same process. Just like last time, we know an angle and its correlating side. We know a side, so let's find that correlating angle. Let's find angle B. Using our law of sines, notice every time I'm using my law of sines, I'm writing it down. That helps me to remember it. It also makes it a plug and chug problem. 22.8 over sine of 55.3. 24.9 over sine of B. Cross multiply. Divide. By the 22.8. And we get that sine B is 0.897868. Now that's what sine B is. That doesn't tell me what B is. How do we figure out what B is? Yeah, we got to do inverse sine. Because if we do inverse sine of both sides, that takes away that sine over here and we're left with just B. So B is the sine inverse of all of this. Now, if you have a calculator that already computed out the decimal, you can type it in and that should be fine. You could also go ahead at this step up here, you could have done sine inverse of all of this jazz to leave it, with as minimal rounding as possible. 0.897868. So we find that B is approximately 63.9 degrees. Now, either referencing our sheet or just thinking for a moment, think about the unit circle. Where is sine positive? So remember, sines are our y values. So which quadrants are our y values positive? Quadrants 1 and quadrants 2. And we just found that sine of B lays between 0 and 1. We're not going to find all the rest of that stuff because it's not necessary. But what this tells us is that sine is positive in quadrants 1 and quadrants 2. We found that this was 63.9. That lies in quadrant 1. So that means there's actually another one in quadrant 2. And the way that we find it is we're going to take 180 minus this, and that's going to tell us our other angle. This is one of those situations where we have 2. So here's the note. That's not how you spell sine. That's how you spell the other sign. Sine is positive in quad 1 and quad 2. So there exists another one. Another angle. And we're going to take 180 degrees minus that first one, which I'm now going to dub B1, to get that new angle. So 180 degrees minus that 63.9 degrees is going to give us B2. So that 116.1 degrees is B2. Now, one thing, though, that we're going to need to check, because we just found this one, and we just found this one. So what we're saying is there's a potential for 2 different triangles, one that includes B1 and one that includes B2. But at the very beginning of this problem, they gave me an A. What do we know about our interior angles of our triangles? They have to add up to 180 degrees. So here's how you're going to check whether or not you're actually going to deal with 2 triangles or if we're just going to deal with 1 triangle. We need to make sure that when we add A to our various B's, that we stay under 180 degrees. Because if we add A to either of our B's and we end up over 180, then that triangle is not going to exist. It's not going to work out. So we need to make sure and check that. So I'm going to take 55.3, which is our A, and I'm going to add to it our different B's. So there's B1. That's 119.2 degrees. That is less than 180 degrees. So that triangle is good. It's going to make. I'm going to do the same thing with our B2. And I get 171.4 degrees. That's less than 180. So it's going to make. We have to do this check right here because it's going to show up later in a different problem that that's not always the case. And one of the triangles won't make. Here, our triangles are both going to make. So we're going to have 2 different possibilities. There's 2 possible triangles that can be derived from just this information, which is why back in geometry and in every other case up until now, we haven't ever played around with these side angle triangles. And it's because it doesn't produce just one nice triangle every time. This one we have a possibility for 2. So we're going to have to consider both. We're going to have triangle 1 and triangle 2. And what we're trying to do is we're trying to solve these triangles. We're trying to come up with all the information. Well, to solve them, we have to have angle A, angle B, angle C, and then side A, side B, and side C. And we already know some of this information. Some of it's given to us at the very beginning of the problem. Like angle A is 55.3 degrees. Side A is 22.8. And side B is 24.9. So for each of our triangles, we're going to have to come up with the other information. But we just found the B's. We found how much our angles are. B1 was 63.9, and B2 was 116.1. Now at this point, I'm not going to go back and forth because I don't want it to be even more confusing, but this is all the information we have. So really the only things that we're missing are angle C and side C for both of these triangles. So I'm going to deal with triangle 1 first and figure out those other two missing pieces, and then I'll go over and figure out the same information for triangle 2. What do you think is going to be easiest to find first, the angle or the side? Yeah, the angle. The angle is going to be easiest because we know that angle A, B, and C have to all add up together to be 180 degrees. And we actually, up here, when we tested our theory, we did angle A and angle B to give us 119.2 degrees, plus C would be 180. So we just need to subtract that from 180, and we find that C is 60.8 degrees. So now what do you think we need to do in order to figure out the side length of C? Well, let's think about what this section is titled. This section is titled The Ambiguous Case of the Law of Sines. So what do we need to use to find side C? The law of sines. So here's what I recommend doing. We know we're going to have C over sine C, and we just found what C was, like the angle C. Now you could, because you have all the information for B, you could use B, but I recommend using the information that they have given you, as much of it as possible. So they gave you angle A and they gave you side A, so I recommend using that, because if at any point in here we made any type of an error, it's not going to get caught if we're doing B and B. So I always use the information they give us as much as possible. So I'm going to use A and sine A. It just helps to eliminate out some of the user error, I guess. So A is 22.8, angle 55.3. We found 60.8. So side C should be, I wrote 22.8 twice. Sine 55.3 is what I meant. C should equal 22.8 times sine of 60.8, all divided by sine of 55.3. So that C is approximately 24.2 feet. That's triangle 1. Now we do those exact same steps, literally verbatim. Exact same steps with triangle 2. So 171.4 plus C equals 180. So C is going to have a measure of 8.6. So obviously this triangle is going to look way different than triangle 1, because triangle 1, angle C was 60.8. All of our angles were pretty close together, almost like an equilateral triangle, equal angular triangle. This other one with the obtuse B makes it an incredibly long, stretched out triangle, because C is tiny. It's only 8.6 degrees. But everything stays. We just changed a few values. I'm still going to use A over sine A equals C over sine C. 22.8. And you might be like, well, why are you writing all of it down? Because then when I go back to reference it later, I'm not questioning where I got any of my numbers, or you're not questioning it if you watch the video later on where any of this information came from. Although this is wrong, because this is 8 and 6. So we find that C in this new one is 4.1 feet. And notice if you look at our information that we've gotten, especially, it's really noticeable on the second triangle, our smallest angle is C and our smallest side is C. Our largest angle is B and our largest side is B. And our middle is A and A, which is what it stated on the bottom of the handout would happen, is they all should line up. So if there's two triangles possible, obviously you're doing double the work in the second half of it. But the work isn't necessarily difficult. You're going to find the third angle that you don't already know using the interior angles add up to 180 degrees. Then you're going to use your law of sines and you're done. So we've seen what happens when there's no triangles. We've seen what happens when there are two triangles. So now we're going to flip over on the back of your handout. And it gives you a little bit more information if you would like it. Honestly, I didn't use like any of this information whenever I was going through and solving the problems, because the way you approach the problems are really the same regardless of if you're getting 0, 1, or 2 triangles. It just comes to a different step where we had sine was greater than 1, so we knew that there was no triangles, or we get sine that lies in between and we find 2 triangles. And now we're going to do the one where we see what happens when we have 1 triangle. So if we have side-side angle, is what it says, in our given triangle, then the law of sines can be used to calculate sine B. That's what we've been doing. If applying the law of sines results in the equation giving B is greater than 1, that's what we did the first time, then we had no triangle. So sine of B is greater than 1, there's no triangle that works. If we get sine of B equals 1, then there's one triangle that works because B is 90 degrees. That's like all the other stuff we've done all semester long when we had a right triangle, not an oblique triangle, and it worked nice. But if sine B lies between 0 and 1, then the only 2 options are we're going to get 1 triangle or we're going to get 2 triangles. So if sine of B equals K, then we can let B1 equal the inverse, use B1 for B as the first triangle. That's what we did, and then we find the second triangle. So step 3 is where we get 2 cases. That's what we just did. So this little box is okay. It's a nice little reference, but it's not anything that we haven't already done yet. Like quite literally, step 1 or number 1 was our first example. Number 2 has been every other triangle we've ever played with. And step 3 is the one we just did. So let's see what happens when we're only going to get 1 triangle instead of 2. to solve the triangle, if we know angle A is 43.5, side A is 10.7, and side C is 7.2. So what are we going to find first? Knowing that we are missing angle B, side B, and angle C. Yeah, we're going to find angle C first. We're going to use our law of sines to find angle C. So 10.7 over sine of 43.5 equals 7.2 over sine of C. So sine of C is 0.463192. So take the sine inverse. And we get C is approximately 27.6 degrees. Now again, we don't know if this is going to result in a single triangle situation or a case like we just had where there's two triangles. And the way, this is like where we determine that. When we find the other angle, because we'll always have to find the other angle because sine is positive in quadrants 1 and quadrants 2, we have to find that other angle, the possible C2 angle, and then we have to determine if adding C with A is going to be under 180 degrees or not. That is when we determine it. Everything else, we approach the problem exactly the same way, every single time. So here, we found that C is 27.6. So if we need to look at C2, the potential other C angle, we're going to take 180 degrees minus the 127.6, and that gives us 52.4 degrees. And just like on the last problem, I'm going to take C plus A and make sure that I stay under 180 degrees. So I take 43.5, that's my A, plus the first C, which is 27.6. That gives me 71.1 degrees. That's way under 180 degrees. So that one's going to make a triangle. We have room to have side or angle B. If we do 43.5 plus 152.4, which is our C2 angle that we're testing, then we are going to get 195.9 degrees, which is greater than 180. This one will not produce a triangle. We're already over the 180, and we haven't even added in angle B. So the only triangle we're going to consider is the one that deals with angle C being 27.6, because it's the only one that makes. So now we know AACC. So what do we come up with next? We're missing B, side B, and angle B. Are we going to find the side first or the angle first? Yep, we're going to find the angle first. A, B, and C have to give me 180. We know A and C equals 71.1. We just found that out. So I'm going to take 180 minus the 71.1, and I find, whoops, that's a B, that angle B is 108.9. So this is one of our obtuse situations. So now we know angle B, angle C, angle A. The only thing we're missing is side B. Law of sines. A was 10.7. Bless you. And we just found that sine is 108.9. Type all that in, and we find that B is approximately 14.7. And it gave it to us in inches.